So now you know that speech can be either voiced or unvoiced, and that voiced speech is excited by a sequence of impulses, and that unvoiced speech is excited by white noise, essentially. And the problem with both of those models is that they're infinite length. Any speech signal that you analyze on your computer isn't going to be infinite length. It's going to be a short period of time. And in fact, if speech was stationary, if it had exactly the same spectrum forever and ever, it wouldn't really be speech. It would just be some kind of sustained vowel sound or sustained fricative sound, which wouldn't be very interesting. Real speech changes as a function of time. And so we need to chop it up into frames and to window each of those frames to be finite length and a finite number of samples so that we can analyze it on the computer. And we're going to do this using something that looks a little bit like this drawing. We're going to cut the speech into frames. So let's let little f equal the frame number, and let's let capital K be the number of samples that we skip in between the start of consecutive frames. And that's not necessarily the same as the frame length. So we usually in speech analysis we want to have overlapping frames. Maybe they overlap by 50% or maybe sometimes by as much as 90% depending on the algorithm that you're using. And if they're overlapping, then they don't need to be rectangular windowed. In fact, sometimes it's useful to window them with a Hamming window or a Hanning window or some other kind of tapered window. And so we'll define w of n to be the window function. The only one that we've really analyzed so far is the rectangular window, which is all ones for a finite number of samples and all zeros everywhere else. But everything I say today will apply equally well to a Hamming window. So the algorithm that we're going to use to chop speech into frames is that we're going to shift the speech by little f times capital K. That is, we're going to take the little f times capital K sample and turn that into sample number 0. And then we're going to window the speech by multiplying it by w of n. And multiplying by w of n will have the effect of zeroing out all the samples except for a finite number. So it looks like this. Here's the speech shifted, and rather than shifting the signal, I've shifted the axis. The sample that used to be sample number f capital K is now sample 0. The sample that used to be fk plus l minus 1 is now l minus 1. This is shifted, but it's still an infinite length signal, so we need to multiply it by a window, which has a finite number of non-zero samples. Here's a picture of a Hamming window. The Hamming and the Hanning window are useful because they're tapered at either end, and that allows allows something that you can visualize either in the frequency domain or in the time domain. In the time domain, it means that the frame is focused on the samples at the center of the frame and pays a little bit less attention to the samples at either end of the frame. In the frequency domain, what that means is that there's less blurring of features in the frequency domain. So each individual harmonic is blurred over a slightly wider range, but then each individual harmonic has less impact on other parts of the spectrum that are far away in frequency. All right, and when we multiply w of n times s of n plus fk, we get the speech frame, s sub f of n, which is s of n plus fk times w of n. All right, now you've seen the algorithm in the time domain. Now I want to analyze it a little bit in the frequency domain. So let's work with an example that's not real speech, first of all, so that you can understand what's going on, and then I'll go to work with an example that looks more like real speech. To start with an example that's not real speech, let's start with e to the j omega naught n. That has as its Fourier transform a delta function in frequency. Plotting e to the j omega naught n in the time domain is difficult because it's complex valued. So here what I've done is I'm plotting the real part in red and the imaginary part in green. And you can see that the real part is a cosine and the imaginary part is a sine wave. And you can imagine, if you like, that the green part is oscillating on a third axis, which is at 90 degrees to the plane of the computer screen. And the Fourier transform of this signal is 2 pi times delta of omega minus omega naught. So it's a continuous frequency impulse centered at omega naught. All right, Now I'm going to window it. Let's start with window number 0, so we don't have to worry about the time shift. So I take a window which is capital L samples long, and the Fourier transform of that window, if it's a rectangle function in the time domain, then its Fourier transform is a digital sinc function that looks something like this. In fact, almost any window spectrum we use will look kind of like this in the frequency domain, with some differences in the frequency at which it crosses 0 and the height of the peak and so on. Alright, so you've already seen then that if I multiply these signals in the time domain, the 0th frame is just the speech signal multiplied by W of n. What that does in the frequency domain is it convolves them. Since this is a DTFT, it's periodic in the frequency domain, so it's a circular convolution. And all that really means, it does mean that we could do a modulo omega minus theta modulo 2 pi, but since W of omega is periodic, that doesn't matter. What does matter, importantly, is that this is the integral over one complete period in the frequency domain. The integral from minus pi to pi, or perhaps the integral from 0 to 2 pi. So here's what that looks like in the time domain. That's the original e to the j omega naught n that's just been multiplied by a rectangle window. And to find its Fourier transform, we have to take that modulation formula and we have to substitute into it that s of e to the j theta is just a delta function, delta of theta minus omega naught. In fact, it's 2 pi times a delta function, which is kind of convenient because it cancels out the 1 over 2 pi in front. And then the delta function has this sampling property. It just, when we multiply the delta function times w and integrate over one complete period, all it does is picks out the value of w at the place where the delta function has its spike. The delta function has its spike at theta equals omega naught, and so we get w of e to the j omega minus omega naught. And that's plotted here. It's just the window function shifted over to be centered at omega naught. So windowing in the time domain has the effect of taking that delta function in the frequency domain and spreading it out into a window, right? Spreading it out into a window spectrum. That kind of makes sense because the whole purpose was to take something that was infinite length and to turn it into something finite length so we could analyze it on a computer. Lo and behold, we've taken something that had an infinite amplitude Fourier transform, and we've turned it into something that has a finite amplitude Fourier transform. So this is a Fourier transform now that could be sampled and measured and stored on a computer. We would just measure it at the samples omega equals 2 pi k over capital N, right? Let's do an example which looks like real speech. Here's an example that's very close to the voiced speech signal that I showed you last time. So we'll say that S of n is some Fourier series. It's e to the j m omega naught times n, summed from m equals 0 to capital P minus 1. So we have capital P different harmonics. And now I'm going to say that the particular amplitude of each harmonic can be arbitrary. I'll call it capital S sub m, will be the mth harmonic amplitude. So its Fourier transform is just the sum of capital P different delta functions, each one scaled by 2 pi times capital S sub m. Here's the time domain signal. It's just some arbitrary infinite length periodic voiced speech signal. Looks like glottal closures with some kind of formant ringing following each glottal closure. The Fourier transform of that event, of that signal, looks something like this. It's a sequence of impulses in the frequency domain. And now, rather than all of the impulses having the same area, now they all have different areas. The area of each impulse is scaled by the corresponding harmonic amplitude of the speech signal. Right, so if we multiply the speech signal in the time domain by Wn, then that means that we do a circular convolution in the frequency domain. And we've already seen what happens when you convolve anything with an impulse. You get W shifted over to the frequency of the impulse. And so we have the summation from m equals 0 to capital P minus 1 of capital S sub m, W of e to the j omega minus m omega naught. Here's the signal windowed in the time domain. You've already seen that. And its Fourier transform now looks something like this. It's a whole set of window functions that have each been scaled by the corresponding speech spectrum harmonic amplitude and added together. So the first window function is scaled by S1, the second by S2, the third by S3, and so on.